Hello everyone, this is Anthony Nunez again, bringing you part 3 of 3 for the tutorial on how to use National Instruments AWR Microwave Office. Once more, this tutorial series is intended for the students of RF Circuit Design at Florida International University and assumes that you have already watched part 1 on the fundamentals and circuit simulation of different things inside of Microwave Office, that you've watched part 2 on how to do optimization, and that you are ready to move on into the advanced subject matter of doing circuit simulation inside of MWO. So today we're going to be covering several points, and I'm going to need to slow down and go very slowly and explain all of this because I need you to understand exactly what it is that we're doing, why we're doing it, why it is important, not just for class but also for your general understanding as an engineer, and also in the case that you find yourself in an interview, you should be able to give the proper answers to these questions. So we're probably going to end up recapping a little bit of theory and just recapping a little bit of material. And so if we're going a little bit too slow, you can just feel ahead to maybe skip around a little bit and find what you need. But I recommend that you actually follow along and try to understand. So the first thing that I need to mention is that today we're going to be doing electromagnetic simulation. This is not to be confused with what we have done up to this point. What we have done up to this point is what is known as the circuit simulation. So the circuit simulation, best way to understand it is we have theoretical equations that describe the behavior and performance of different components. And these theoretical equations give us a ballpark, pretty solid idea of, again, how these components behave. However, they are not 100% accurate. So normally, for example, in normal circuit theory and in circuit analysis, low frequency circuit analysis, for those of you that have taken circuit analysis, electronics 1, electronics 2, you learn about Kirchhoff's voltage law, Kirchhoff's current law, you learn about Ohm's law, you learn about these things. However, these things are not applicable across all frequencies. There's assumptions that you are making. So for example, let's be very specific. When we first define Kirchhoff's voltage law and current law as far as circuit analysis is concerned, we actually made an assumption that we didn't really do a good job of explaining early on in the coursework because it would confuse people. And this assumption is what we call the lumped element assumption, or also known as the lumped element model. This assumes that the wavelength of our signal is many times larger than the physical size of the component. So when the frequency is low, the wavelength increases. They're inversely proportional to one another. And this means that, for example, our resistor might be a few millimeters long. However, the wavelength is many meters long. And as a result, as far as the signal is concerned, that component looks like one solid block. And so we make all these equations, we make all these assumptions when we use our basic theory, and this gives us the base that we build upon. We get to RF, we get to microwave frequencies, we no longer make these assumptions. Now we know that the wavelength is either very close to the physical size of the component or it's less than the physical size of the component. So the lumped element model no longer applies. We come up with new equations, and as we learned at the beginning of the class, we kind of try to bridge the gap between Maxwell's equations, which are the most accurate equations for representing the behavior of these components. And we try to bridge them to what we already have. We came up with the telegrapher equations and these different equations for describing the behavior of transmission lines and components. And so this, in the process of creating this bridge, we have effectively introduced uncertainty, we've introduced error, because again, we're having to make new assumptions that I'm not going to get into. The less assumed equations, like the telegrapher equations and so on and so forth, are the types of equations that are used for the circuit simulation in a software like AWR. However, they are not 100% accurate. Maxwell's equations are 100% accurate. And so as a result, if we want to have as close to 100% accuracy, as close to real world performance and the idea of how this component is going to behave, we need to do an electromagnetic simulation. We cannot do a circuit simulation. That starts introducing assumptions and things like that. And so we need to do the electromagnetic simulation. This is going to give us the best estimate of how our component is going to behave in the real world. Thankfully for us, AWR can do EM simulations. I could get more into EM simulation as a whole and 3D versus 2D and these different things, but I'm not going to get too much into it in this video. All you need to know is that this is a 2D simulator. It is not a 3D simulator. A software like ANSYS HFSS is a three-dimensional full-wave EM modeler, and in that program you will get even better estimates on the performance of the component because you're taking all three dimensions into consideration. In a solver like what we'll be using here, you're basically slicing your component into 2D slices and you're solving those, and so as a result you're again introducing a little bit of error. However, this gives you a pretty solid guess at how your component is going to behave. So okay, that brings us to point number one, the method of extractions. So we have different ways of creating the EM simulation. However, there is one that is native, that is something that the National Instrument people, the AWR people, came up with, and I love it. It's great. It's amazing. It speeds this up so much for us, and it's known as the method of extractions. And I'm going to show you just how easy it is to do this, and it's going to blow your mind. So what we're going to do is we're going to bring up our circuit that we've been working on up until this point. And I'm going to go very slowly here, guys, because this is going to blow your mind. You're going to go up to the toolbar. You're going to go to scripts. Under EM, you're going to find a script called Create Stackup. All you're going to do is click on this. And then you're going to get this window. It says AXIEM Setup. Select Substrate. In the drop-down menu, we only have one substrate. It's our FR4, so we leave that as default. We will change the grid to 0.01 millimeters. This has to do with meshing and EM simulation things that we're not going to get too deep into. Just for this simulation, 0.01 works just fine. And so we're going to go ahead and we are going to let this set the stack up for us. And when you hit OK, you'll notice that now we have some new components. We have a stack up block and we have this extract block. You might be wondering to yourself, what is this extract block? Well, what you've been looking at here in layout view is what we would typically Control-A, copy and paste into our EM project inside of AWR. The extract block will actually pull out these components, turning them into the layout and auto-exporting them to the EM simulation. You don't have to do it. Every time you make an update in the circuit view, it will automatically extract those updates, those components, those parameters, sizes, values. It will automatically extract them into the EM document. And when you hit simulate, it will automatically do this extraction, run the simulation EM, not circuit, but EM, and give you the results as if you were doing a circuit simulation. So you get to basically abstract away the complexities of doing the EM simulation, and it's basically almost the same as doing the circuit simulation. It just takes a little bit longer because there's a lot of math that goes into it. Again, I'm going slowly because I'm trying to explain this because I need you to understand what is going on here. That is what is happening. This is extracting out everything that is needed to do the EM simulation and doing it for you. There's a couple of things that we need to do. Let's understand something. Let's go here into the stack up, where we're going to double click on it. This is going to bring up this window here. We're going to go to the first tab called Material Definitions. Typically, when you're going to do an EM simulation, you have to make your own stack up. And typically, you'll come in here and you'll edit the values yourself, and you'll put things in here and you'll do whatever you need to do. You will see that automatically the script we ran extracted out the dielectric definition. Again, these waves at RF and microwave have to propagate through a medium. So for example, between two radio antennas, two FM radio antennas, for whatever radio station you like to listen to, if you still listen to radio, the waves will propagate through air. In a coaxial cable, for those of you who live in Florida and you have Comcast, Xfinity, the signal for Xfinity comes to your house in a coaxial line. The signal propagates through Teflon. Most coaxial cables are the dielectric used, besides copper as the conductor, between the outer copper shielding and the internal copper wire, there is a sleeve of Teflon, and that acts as the dielectric, as the medium by which the wave propagates. Instead of being air, it propagates through the Teflon. In this case, the wave is propagating through the dielectric FR4, which is a type of fiberglass, and it has a dielectric constant, which is 4.4, and a loss tangent of 0.018, and these different quantities, and you can get all kinds of different dielectrics. In this case, we arbitrarily chose FR4. FR4 is typically used for PCBs, so when you get a PCB, or you open up an electronic device and there's a PCB, a printed circuit board inside of it, it is most likely some variation of FR4. And it's also cheap and it's widely available, and so it's great for prototyping. That is why we chose FR4 arbitrarily as our dielectric. We see conductor definitions. The most common conductor used for these kinds of circuits is copper. You can use others. There's silver and gold and all kinds of other conductors you can use. However, in this case, we are sticking to copper. It's cheap, it's widely available, and it is something that we can use confidently, knowing that we'll be able to find it. The next tab gives us the dielectric layers. This is how we tell AWR how our sandwich of dielectric and copper and air is set up. And so here we're basically telling it that we have a top boundary, which is above the sandwich, a bottom boundary, which is below the sandwich, and a side boundary, which is on either side of the sandwich, and it's basically, think of it like the walls that limit our sandwich, right? So we're saying here on the bottom, we're looking at the top side and bottom boundary, we're saying that the top boundary is approximately open. This has to do with how the wave propagates and how the wave sees the upper boundary, and it's basically an open. Think of it as you're looking at your PCB. What is above the PCB? Air. So air, just open air. So it's approximately open. The bottom boundary, right? So you look at the bottom side of a PCB. Most PCBs have copper on the bottom as well. So what is the bottom boundary? Copper. The side boundary, this is where it gets a little bit more technical, right? We don't have an infinite sandwich, an infinite piece of board that we're working on. It's finite, right? So we prefer to have the wave see the edges as a quote-unquote perfect conductor. If you want to learn more about why we do that, you can go more into EM modeling theory and so on and so forth. That's basically the idea here. So then we have our bottom conductor as copper. We have a 1.524 millimeter layer of FR4, and then we have 250 millimeters of open air. We actually do not need that much. We can actually lower this, and it's actually going to help speed up the simulation a little bit. But for the sake of argument, again, we actually don't have to fiddle with these settings. We don't have to touch anything here. I'm just showing you what this all means, so that if someone were to ask you, please explain how this works to me, you know exactly how it works. So we're not going to touch it. If it takes a while, it takes a while. If it's fast, it's fast. If it takes a while, it takes a while. So let's do that. Materials. So here we define the materials. we have some definitions here. So copper, Cu, has a thickness of 35 microns. It's the material. We pick which material it is, copper, right? And then obviously we used perfect conductor for the side boundaries. So that is also going to be defined here. EM layer mapping, this basically just does, this is more for when you're doing PCB design and you're going to be doing designing boards. This is where you have all your layers so that you have your vias and all kinds of other things that would come into this. And at this point, we're just going to hit OK. And we're going to close that and we're going to stop worrying about it altogether. And we're going to open up the stack up block. Okay. Frequencies. It is using the standard default frequencies from the project. It just copies them directly. However, EM simulations are slower. So sometimes what people like to do is they will use the same frequency boundaries. So in this case, we said 4 to 5. And previously, we said 0.02. In this case, we're going to say 0.05 and replace. This is only 21 points. This will give us a rough idea. If we want more accuracy, we can come in here and change this back to 0.02, and that's going to give us the more fine result. We're going to look at the meshing, basically just a quick explanation. Basically how this does it is solving Maxwell's equation as is of a solid, of a design, of a shape as a whole is difficult. It's a lot easier to slice that shape up into pieces and solve small pieces and then bring all the answers together into the big answer, and it's basically a lot faster and a lot easier. So meshing has to do with that. We're not going to touch that. We're going to go to AXIEM and we're going to look at this and be like, okay, cool. So here, what are we looking at? All right. We're going to go down here to the bottom right and we're going to hit show secondary. This is important. We're going to go to auto port setup and we're going to look for a setting, and I always forget where the setting is, and I should have looked for it before making the video, because if you don't put this in correctly, this is not going to work properly, and it's just a huge pain to figure out why is my simulation not running correctly. It is because this setting is not correctly configured. Okay guys, we were in the wrong tab, in the parameters tab, which looks a lot like the standard parameters window for all other components. There's a couple things we need to edit here. First of all, in StackUp, we need to select sub 1. That is the special StackUp that our script created based on our MSub microstrip substrate. And also, here we see explicit ground. This we need to set to connect to lower. Why? We need that when we are quote unquote exciting the port, think of the ports as where you are feeding a signal in or getting a signal out of. We need to make sure that the signal, that the wave is propagating between the ground plane and the top conductor. And the only way that this is going to happen properly is if we say connect to lower. So it's basically going to make sure that we are exciting the port between the top conductor and the ground conductor so that the wave is propagating through the dielectric, which is basically how microstrips work. So that's what you need to know. So again, I closed the window. Let's open it again. Double click. Frequencies. I changed the step size. It's going to make this go a lot faster. I came to parameters. I set the stack up to sub 1, and this is something that I didn't show, is you need to click on second up here. This basically shows secondary parameters. I'm sorry about that. That brings that up. And here where it says explicit ground, we make sure that this is connect to lower. It has to be connect to lower or this will not work, and we hit OK. Then we look at our design. Awesome. We have not touched this at all. We are going to go ahead and hit simulate like we normally would, and we let it run. Okay, that ran. Nothing happened. Why? Well, you will see why. So we have this extract block that is supposed to automatically extract components, but we haven't told it what components to extract. So as a result, we're going to shift click all of these transmission lines and the microstrips, but not the resistor. The reason why we're not going to put the resistor as part of the extract block is because the resistor is not a EM compatible component. And so what's going to happen here is that you're probably wondering, Anthony, how can we not include the resistor? It's an important part of the design. We need it to be there. Yes, what's going to happen here is that AWR is very intelligent. It's going to realize that you are connecting this resistor between the quarter wavelength segment and the half wavelength segment. It will actually automatically create another set of ports at that place. It will bring the results in intelligently. Instead of being a 3-port network, it will be a 5-port network, and it will put the resistor between the appropriate ports in order to run what we would call a 2.5D simulation. It's a bit of a hybrid between EM2D and circuit. And it all works out. It gives you pretty accurate results. So once we've selected all the components, you right click, Properties. You will go to Model Options, Enable EM Extraction, and make sure that we select the only group name that is available before hitting OK. Then when we click the extract block, we will see that our components highlight in red. This means that when we hit simulate, these components will be extracted out into an EM simulation, and the simulation will be run. Now when we click on simulate, we notice that now it doesn't happen instantly. It takes a little bit of time, and as we can see here, it has automatically created for us our layout. It has put the appropriate ports and everything, and we can see it running. Now while that is running, I want to bring your attention here to the transition point. You will see that there is a magical port that has been automatically placed in between the quarter wavelength leg and the half wavelength leg. And that will be for putting the resistor. Now, I'm going to let this run, and then we will check our results to see what happened. Okay, so I canceled the simulation and checked something because it was taking a long time. Okay, so what I'm showing here is the mesh. This is the little cubes that our design is being divided into, and you can show this by clicking up here in the toolbar the button that is labeled mesh. It's that button specifically. It's not currently showing the actual results, and there's some error messages and stuff from that from me actually clicking on this. And what we can see is that these squares are very fine. They're way too fine. They will make this simulation take forever. So what we can do to fix this is we can go back to the circuit. We go to the extract block, and we change the X cell size and the the X and Y cell sizes. Let's make this 0.1 millimeter. Let's see what happens there with that. We go back, let's right click on this, add extraction. That will regenerate the EM project. And then we'll go ahead and regenerate the mesh. And now it's a much better mesh. I'd argue we may even be able to go a little bit less fine than this. Let's try 0.2. And then just right click, add extraction. We'll go ahead and regenerate the mesh. And okay, this is much better. So now we will go ahead and hit simulate. And this should move this along a lot faster than before. All right, now we'll let this run and then I'll be right back. Okay guys, that ran super fast. Yeah, so that meshing, that's important. Gotta get the right size of that. But hey, again, you get to watch these mistakes happen live, and you know, I know how to fix them. If you had bumped into that by yourself, that would have been a huge issue. That first time, that took me forever. So now, transmission, what are we looking at? All right, cool. So okay, let's disable the goals. You can simply right click on them and hit toggle. I will get rid of them, and trying to find the line here. 3.47. Okay, so our actual transmission, port 1 to 3 and port 1 to 2, is around that 3.5, negative 3.5 dB mark that we were expecting. Our isolation is actually not as deep as we were expecting last time. Again, it's the discrepancy between a circuit simulation that's more theoretical and an actual electromagnetic, more realistic simulation. If we go to match, we can see that thankfully all of our matches are actually pretty flat and sub negative 20. So this is very good for us. We can see that there's not a lot of weirdness going on, so I'm not even going to bother actually doing any kind of finer frequency stepping. I think this frequency step shows us all the information that we need. Let's say that we wanted to do optimization on this. Okay, we already have our goals, we already have our circuit, we already have this. Guys, this is how easy this is to do when you are using the method of extractions, when you are using the extract block. You want to know how to do this? Easy. Simulate, optimize, and hit go. It is exactly the same as doing the regular circuit optimization. The extract block makes it so easy to use the optimizer on your EM simulation. Obviously, this method of optimization is going to take longer because EM simulations take longer. One thing I did not explain last time is that the optimizer basically runs the simulation once, and through the determined algorithm modifies the variables you have chosen to optimize in some way. Runs the simulation again. It sees if it's closer or farther from the goals you have set, and accordingly will again adjust the variables. Run the simulation again, make adjustments, run the simulation again. Each time it runs the simulation, obviously, if it's a circuit simulation, it'll be a lot faster. In this case, it will be EM. It will take longer. Depending on your meshing and your frequency step, your frequency range, it could take a long time or it could take a little time. With my graduate research project, this can take easily a whole day. So normally I will leave these optimizations running over the weekend because it takes time. In this case, a two-way Wilkinson power divider is not that complicated. So we can run this in a matter of seconds, maybe a minute at most. And so seriously, that is literally the optimization. So if you wanted to optimize these results because you wanted to get better than this, then you could easily just, again, fiddle with the variables, fiddle with this, fiddle with that, and use the optimizer as you learned in part 2. There's literally nothing else for me to teach you on how to do optimization for EM, because when you're using the method of extractions, it makes optimization incredibly easy. There's nothing else for you to learn. It's the same as for the circuit. So today you learned about why we do the EM simulation. This is in general. This is not just for AWR. Why we do the EM simulation, why it's important. The method of extractions, how AWR makes it incredibly easy for us to do EM simulation, specifically 2D, two-dimensional simulation. The fact that this enables us to do what we would call a 2.5D simulation. It is a hybrid between EM and circuit. How the EM simulation is set up in terms of meshing and the frequency sweep, and how we set up the extract block so that it properly extracts things. And finally, understanding that EM optimization in Microwave Office is incredibly easy when you're using the extract block, because basically it makes this behave like a regular circuit simulation, but it's actually EM. And so we can just do regular optimization like we did in part 2 on an EM circuit. And this basically has set you up to do your project. If you watch all 3 parts back to back in a little over an hour, you're going to be set ready to go to do your project, or basically design any RF microwave circuit using AWR. If you have any questions, please leave them below in the comments, or reach out to me in class. I'd be more than happy to answer them for you. Thank you for watching this video. Thank you for watching the other 2. And I hope that this series has given you the proper primer that you need in order to feel comfortable using National Instruments AWR Microwave Office. Thank you, and see you next time.